What we've alluded to a few times over the past few days, but haven't really gotten into in detail, is how do I take images from different detectors, different channels on even on one telescope, and line them up. We want to see wave propagation. We want to see how these bright points in the photosphere go up and what they're doing in the chromosphere. So we have different wavelengths we're observing at the same time. Even with VBI, we have the red and the blue channel, so you can have different channels going at the same time. There'll be different filters rotating in, and we're lining things up now, to a few pixels, right? And those few pixels are now a few hundredths of an arc second with DKIST. So we need to be careful in getting these things co-aligned. We also have very big detectors, 4K by 4K detectors. So little 1% errors are now 40 pixel errors in your images. So I'm not here to scare you, really. I'm here to tell you there's hope. It's possible to do all these things, and we have the tools and there's ways to do it, and we'll all learn together how to do them at even higher spatial resolutions with DKIST. And so, we have these channels we want to line up. We have the white light channel over here with IBIS, this, that same data set I was using that Juana can attest to, that you can get these things lined up as her nice results were showing. We can see these, combined multiple channels. We have the G-band. We have the Rosa continuum at a different wavelength. And so we need to line these up. Yes?
Are we going to be talking exclusively about co-located things or other things that are next to each other?
We're talking about co-located. We're trying to get our spatial coordinates, basically, and we have two images. Each one, as it was observing the sky of the sun, it had a different sort of spatial coordinate system mapping, and we want to get those two so we know those the same. Some of this, and I don't think anyone knows exactly how much, will be done as part of the standard processing in the data center, right? There'll be some of this mapping and making sure there's some co-alignment. How that will be done exactly and how accurate that is and so on, I think is all sort of a TBD at this point, and as all the procedures are tested and what's possible to run in an efficient time scale in the data center and so on. So it may be that some of this is sort of done for you. Again, it's good to understand what goes on, even if you get nice co-aligned or partially co-aligned data, what's already been done, and understand what's going on in the background. So to first blush, you'd look at these and say, okay, well, I can co-align those. They're pretty much both granulation. How hard can that be? I can just put them on top of each other. We did that yesterday with the de-stretching, where we took one image and another image of the same scene and co-align them. We could do that with our G-band and our white light image, and just do a de-stretch and get them lined up, of course. Now that, in part, that's true, but the complication comes in when I start observing in different wavelengths. And here's an example now. I have a Rosa calcium K image, and it looks nothing like my other images. So I can't just try to line up features and map this onto the other one. We'll have this with the VBI. We'll have images in alpha. There'll be a lot of chromospheric structures. And so we can't just use the images themselves to do that mapping. We're going to have to use some external calibration. And the one we've worked on primarily with the DSP, and getting this alignment very accurately done, is what we call the dot grid. It's a nice uniform grid of dots, and it looks kind of the same in these different channels. Obviously, you see down here, this is the Rosa continuum. If we take it at a higher resolution, that's why when I match them here to the line, it gets smaller. They have a higher resolution than the original sample. The dot grid is now the original sample, and now the grid is zoomed in a little bit and stretched farther apart. What I can do is I can measure how far apart these dots are. These are all taken with the same dot grid, same time on the telescope. I know they should all be exactly the same sort of pattern. And I can
can measure and see how far apart the dots are, and that should tell me the relative image scale or plate scale between these two. Yeah, is that like so this is a tiny this is a piece of glass, and it's got some dots put on there. Swiss company, so it must be very accurate. And it's glass, and so they have a solar light coming through the background. You can sort of see in the calcium cave, you see the sort of solar structure in the background. So this is placed in the prime focus of the telescope, the solar light. Not in the prime focus. Not as big as well. The DSP is in prime focus, and the DSP is in the secondary focus, the first focus of the telescope.
So this type of dark grid will be taken before and after the observation?
We normally do it just once during the observation. Yeah, we definitely do it before we move anything. We're changing the optics.
But basically, you don't have to request it.
You don't have to request it. This is something now that's done. And again, they may take this kind of calibration and apply it, and when you download your data, your level 1 data, there won't necessarily, you may not get a doctor. Done, or request or something. But the data will be taken and used to the on the data station. And so, at the DSP, it was then handed down to generations of the first scale, 2.7 parts seconds per millimeter. Comes from the focal length of the meter, basically. And so these dots are half a millimeter apart, or half a millimeter apart, and so we can get the first scale, after the first scale, the image from that. So that's one thing to get is the plate scale. There are other sort of alignment issues that we can also look at with this kind of calibration. I mentioned unit scale, and that may be different in different directions. That's why unit scale may be different. It may change from day to day. If you put in any kind of object, if you put in a beam splitter and if you change the configuration, you'll see changes of less upper text or something in your plate scale, but again, it's one rather sizable number of pixels in a tiny image. There's also rotation. I have rotation between my different channels that I want to look at. How the detector will come in. I have different mirrors in my optics. So these are sort of the primary, and also the pointing. So the dot is the center of one dot. That's the same position in the other image as the same dot. Then there's some second order effects that you may or may not have to worry about depending on the time. There's optical distortion
In there that you can see with this grid. If that plate spacing isn't uniform and across the whole image, then you can see that with the grid. And there's also sort of, there may be time-dependent shifts in rotation. At least we see that in the DST. It's a 50-year-old telescope. Hopefully DKIST will be more stable in that respect. So how do we go about calculating and doing this? How do we get from this grid to get all that information out? And it's fairly straightforward. We have a program here. And so I'm just going to, there are commands here for doing this. This is up on the Google Drive, and they're in a folder in the home workshop, Reardon exercises dispersion. You can find these commands as well. But in the interest of keeping everyone awake, we're just we can run through these up here on the screen and see how see what this does. It might be more illustrative. So let's see what the effect is here of the different plate scales. Let's see. That's going to work. There we are. So this is the G-band image and a white light image. And they're flickering back and forth here. I'll just point out this is running on the server. Retain equals 2 is magic, and it makes it go a lot faster. So you see here as it goes from the white light, the G-band has been shifted to line up there, so you see the gray bars. And you see that different scale, right? In the center of the image, they should be pretty well lined up, that same granular layer. Bill is right there. Francis is over here. But you see the scaling, and it's in which direction, is the primary image scale difference here. It's expanding up in that y direction. So the x scale is pretty close, it looks like, the eye tells us, and then it scales up in that other direction. So we'll use our dot grid to get an exact measurement of what that is. So we have saved some dot grids here. And now we will run a command here called find dot grid spacing, which will find the dot grid spacing here. So there's my, get that over there. So this is my dot grid. And it can't see it up here, but it asked me to click on the dot in the lower left. So I click on a dot here in the lower left. Anyway. It's confused by the size of the window is not correct. Okay. Give it a second, see if we can make it smart. Well, the image is 1,000 by 1,000, so you would think that would be the right size, which is what it should have created the window as. Okay. One more time, otherwise we'll just move along. Yeah, see, it doesn't. It has. But yeah, just not. Okay. Well, what it does is it goes through and finds all the dot positions. Not very exciting. And it gets all the dot positions in there, and then measures their relative location, and then the image rotation between from the position of the dots. It can also determine the rotation of the grid. It sees if the dots are if they're going in a straight line or not, and it determines the rotation and the plate scale. And so from that, so we have the numbers here. So it gave me I did this before, and it determined the rotation here between these two for the G-band and the white light image. And it indeed found that the X scale was very close to being the same, but the Y scale was significantly smaller. And so I can just use those values it found before and calculate this. Mhm. And now we can look at these two grid images. This should work, perhaps. So now I have the two grid images. You see they're pretty close. The grids aren't changing, right? The different, everything's pretty close to being lined up between these two. There's a slight shift, it looks like there. But that's easy enough to take out. So we can use this. We get the plate scale and we can scale one image with respect to the other one and get them pretty close to being lined up. And the accuracy, you have 40 by 40 dots in here, or 50 by 50 dots across this field of view, and so you have 1,000 measurements plus measurements of the spacing, and so your accuracy is within a part per thousand at least in the image scale, the average image scale across the whole field of view. So that's good. So we are able to determine that quite accurately. Now the other part was I have these two grids. There's another way to look at whether they're precisely lined up here. I can take the flicker's nice, but I can also take the divide one by the other, right? And so you can sort of see here. So when these aren't lined up, you see a rather significant sort of offsets, right? The two should, if you're not lined up, you see this, right? This is the original grid. So if I just divide one by the other, I see in some places, right here, the two dots lined up quite well. But then as you move up, right, as you move off of that point, now the dots are off significantly, and in the opposite direction, they go the other way, and then they happen to match up again when you're, the scaling is off enough, and then they separate again. So you get this pattern of light and dark, and that, visually tells you, oh yeah, these aren't lined up in some places, so there's a scaling problem. Again, it's all a vertical scaling. But when we do this after measuring the plate scale and lining it up, things look pretty nice. You see some, the errors are much smaller, the differences there, that white and dark. But you still see that in some places, they cancel out almost completely over here, but there's, places here where I still see that a residual effect of this offset between the two dots. And to go that next step in the alignment, if it's important, you can actually basically do a de-stretching between the grid images, and that will tell you that de-stretching, instead of telling you the instantaneous sort of image motion caused by the atmosphere, will tell you what the distortion is between the two grids. And if we do that, and here it is measuring, and it's showing, with the de-stretching, it has this pattern of grid positions, and it's going through and measuring the relative offsets in each little sort of position across here. And give it a second. It's very slow when it displays. Cover it up. And so now, when I divide these two out, I'll do the same thing. I'll divide the de-stretched grid to the of the G-band to the white light grid, and we'll see if that improves things. And so that gets me to that corrects this sort of optical distortion we were talking about, where because of lenses and glass and various things, you have a fixed sort of distortion between your images. And find my cursor here. So now when I take this, oh, well that made it worse. Did I do the right thing? Oh, yeah. Yes. Oh, that's between the de-stretched grid and the non-de-stretched grid, so hopefully this is between the IBIS, the white light grid, and the G-band grid. And now, yeah, now it's much more uniform. You still see it's light. Now the dots here are all white, sort of. That's just because the depth of the dot, the more scattered light in one channel than the other, but there's no sort of that black and white indication of a relative offset. So now all the dots are very precisely lined up, and I have a good mapping of my image everywhere in the field of view, or the image scale everywhere in the field of view, and I can apply that if I want to all my images and get them mapped back out onto a nice rectilinear grid and have my coordinate system properly defined. So that is how you can take any channel that you can apply that grid from the calcium K channel, get the spatial scale precisely determined, and remap the calcium K, and then it's at the same plate scale as all your other channels, even if the structures in your individual images are quite different. When this kind of calibration using an internal reference, this dot grid, is important because we don't have, in some cases, the images in two different channels are very different solar scenes. One shows the photosphere, and another one will show the chromospheric structures in H alpha or calcium, and so we have no way from the solar images to get that alignment precisely, so we use an internal reference here. Now we can, there is again an external reference we can use here if we want to know something exactly what the plate scale is. So this was this canonical value of 3.76, and that we can map everything assuming this dot grid was, the Swiss were precise, and this was a 0.5 millimeter, and that's the actual plate scale. But we can also get the absolute image scale, if you like, or a better reference image scale by doing a mapping to HMI. And this, we just need to do once really and make sure our dot grid scale is accurate, but we can map to HMI, and we know what HMI's plate scale is to some level of accuracy, but at least it's a sort of a standard reference. We can map our image to that and calculate what the plate scale is with respect to HMI, and do get an absolute calibration of our image scale. The other thing we can use HMI for is to look for, yesterday I talked about how we can look for drifts over time, take all our images and line them up. Once we've done that, we can also take our images and do this alignment with HMI, but look for any rotation. And so we can take the image and map each image over a time series to HMI and see if that mapping changes. The plate scale shouldn't change, but sometimes there are rotations. There's a lot of moving pieces in these telescopes. We're compensating for the rotation of the image in the telescope by moving the Coudet table and so on. And so sometimes there's some residual rotation in there, and we can, the only way we can sort of look for that, because we don't have a fixed reference, the dot grid is always going to be in the same orientation, we have to look at some external reference for that. And so we use HMI. So, that's basically different steps we can use to, to get our alignment between different channels done accurately. And using, internal targets like this is the way to go. And again, a lot of this should be done, or there should be tools we're developing to do this alignment and help with this. So it may be something you see, and hopefully that will be fine, because now you know what it is. So what happens now, if we have the plate scale corrected here, that is the level C should have the So this was level B images in those data that are on the Google Drive or on the server. Level B is all the plate scales were different, the rotation wasn't of the different channels wasn't taken out, and so on. Now we have in level C, all the plate scales have been mapped according to this dot grid to the same scale, and the images have been co-aligned according to the co-alignment that comes from this optical, this internal reference. And so let's see what happens when we compare so this was, go through it again here. So this was the before the plate scale correction. Right, you saw this. So much faster. There it is. So you see the plate scale jumping there. Okay, that was level B. Let's look at level C, where this has all been remapped in our image. And so these are all remapped. And now we should have the same plate scale. But there's a problem, right? So let's find a granule here. We'll call him this guy here. Jumps down here, he's up there. So I took the grids, I mapped where a part of the image in one grid was in the other channel. I line those up, and then I do this, and I do this to both my images, apply that correction, and now I see there's a big offset between the images of the sun. So why is that? We have to go back. It's our atmosphere again, causing trouble. So we will cover that now. So our atmosphere has something, as you probably know, something called refraction, right? So we have, as the light comes through the atmosphere, it gets bent around by refraction, and so the image we see is not, light isn't coming in a straight line, it's bent, that's fine. The magnitude of the refraction, of course, increases as we get closer to the horizon. And it's coming through at a more oblique angle through the atmosphere. If you look straight up, of course, you wouldn't have any refraction effect, but here we do. And it gets to be quite significant here. Below an altitude of 30 degrees, that refraction is already, or wait, that's 30 arc minutes. The refraction is already quite significant, up to 30 arc minutes, 40 arc minutes. So there's this big change in the path of the light through the atmosphere. That does some neat things. So one, and they're most obvious at sunset, of course, when you're going most obliquely through the atmosphere, and there's a long path length. So over here, refraction, right? It's causing the light to be bent, so lower down in the atmosphere, the light is being bent more and being lifted up. So it actually causes things. The sun is actually, when you see it set, it's already actually below the horizon, and you're seeing the refraction is pulling it up. So sunset actually occurs later visually than it does, from a purely geometric standpoint, and that also causes, it's pulling up the lower border of the sun, and causes this squashed sun at sunrise and sunset. So refraction is, it's significant. And it also has this effect here that we'll talk about, where you see the green flash. I don't know if has anyone ever seen the green flash? I thought I did once. It's probably easier from here in LA than in other places. So what is the other fact? So this refraction is, a problem close to the horizon. That's one reason in nighttime astronomy, in addition to the lower air mass, they always observe when things are high in the sky, so they don't have to deal with some of these refraction effects as much. As we saw, though, the sun, the best seeing is early in the morning when we're observing the sun from the ground. And so we try to observe when the sun is very low in the sky, not far above the horizon. So if we observe 1 or 2 hours after sunrise from Dekist, the sun is only up 15, 20, 30 degrees above the horizon, which is still very low from a astronomical refraction standpoint. And we could deal with that. I mean, the actual absolute refraction of the sun and tracking the sun is all done automatically by the mount, and it all knows the magnitude of the refraction and how to track the sun. So that's not a problem. The problem goes back to this here, this dispersion effect, right? So here the red sun, the red part of the sun sets sooner because its refraction is a little bit less, and the green part of the sun, the green wavelength of the sun sets a little bit later, and so you get a little separation of the solar image according to wavelength, and you end up with the green flash, hopefully, if you're lucky. Go the other way. And so this is a problem because what it means is we have a wavelength dependence of our refraction, and so we can't assume the same part of the sun appears in the same place in the sky at all the wavelengths. And it's basically because the index of refraction depends on wavelength, and that's much more significant in the blue. So this is wavelength down here, so we're down here at 4,000, 3,000 angstroms. This is the magnitude of the refractive index over here, the refractivity, and then it drops down, and as we get out into the infrared, this problem's much less, but if we're observing anywhere down in the visible, the refractivity is quite high. And so what does this mean in terms of our dispersion here? That means as we look lower in the sky or at different wavelengths, we see an offset between two images. And that can be, even in typical observing conditions, can be several arc seconds, depending on the separation in wavelength and the altitude. And several arc seconds is a significant amount, even in with today's observations. You saw it there. That's why those two G-band images, the G-band and the white light images, were so far apart. All that was atmospheric dispersion, causing those two images to be shifted in the sky and hence shifted when we looked at them. So I lined everything up on that grid, but that's all an internal alignment. It was nothing about the path length through the atmosphere. And so the telescope is, in effect, imaging different parts of the sun when it's looking in different wavelengths, because it's always pointing in the same direction, but different parts of the solar image are being observed in that same direction because of the dispersion. So we need to find a way to deal with that. One just mentioned some other effects here with the dispersion. It can cause some smearing in our when you're imaging through a filter with a significant bandpass, right? If I have a few angstrom 5 or 10 angstrom filter, again, I have images being sort of spread out according to wavelength, and that will sort of spread out the image across the filter. So my PSF, these are the PSFs, sort of what Jose was showing yesterday. This airy rings around the PSF. This would be a nice perfect PSF with the rings around it. And here you see there's some smearing, and as you use broader filters, you see some smearing in that direction. So even with a G-band or a continuum filter with, and this is with a 4-meter telescope, observing fairly low, only at a 15-degree elevation, but you see there may be some anisotropy in your PSF that hopefully you don't ever have to worry about, but if you're measuring bright point structures, you may start to see them sharper in one direction than the other. The other issue is that there's the direction of this dispersion doesn't stay lined up in the same direction on the sun all the time, right? So in the morning, I see the sun is coming up over here in the east. Sort of solar north is pointing off that way towards the celestial North Pole, or close to it, depending on the P angle. This is the celestial North Pole. And then we have the solar P angle that changes slowly during the year, so that's constant more or less during the day. But the direction of the dispersion is always perpendicular to the direction towards the horizon. And so that's this yellow arrow. And so later on in the day, as the sun rises, now the solar image sort of rotates. Celestial North Pole now goes up through the zenith at local noon, and now my dispersion direction is still along this direction, but that's changed with respect to my solar coordinate system, and it falls over in the opposite direction. If you observe all the way to the afternoon, what does that mean? That means that that offset, the directions of the offset between any two images, is not going to be always in the same direction. The magnitude of the offset will depend on the angle with respect to my solar image. And so when the sun is rising, now I have a shift primarily in the east-west direction, and my north-south shift is small in the morning, right? Because I had all my direction, my dispersion direction was in the east-west direction on the sun. But as we get to noon, now the dispersion is going more north-south. But also the magnitude of the dispersion is decreasing, so it gets fairly small. And as towards the afternoon, now the dispersion pushes off and is more north-south. And so it has sort of different trends. And this is for one specific day. A different day would have a different trend. But that's okay. You don't have to worry about that, just to know that it changes with time. If you're observing, so here we've been talking here about imaging instruments like VBI. We have those G-band images, and we'll see how to deal with the problem there. There are other instruments on DKIST, of course, that will have other issues with the dispersion problem because their field of view is so small, and so you have to. It's going to become harder, perhaps, to deal with some of those. Slit instruments, of course, your slit is a one-dimensional slice, and now you have shifts with respect to that. So. That'll be hard to deal with, or you'll have to be careful in planning your observations. The other one, here's an example with the DL NERSP. So this is the one that has this little fiber, and you can take a very high resolution little cutout of the sun and put an array of 60 by 80 fibers here, put those through a spectrograph, and so you get spectral information and spatial information all at the same time. But if you want that at the highest resolution that DL NERSP can provide, your field of view is only a few arc seconds across. And a few arc seconds was sort of typical sort of the scale of the dispersion that we had. And so this is what happens, is you have these different images, and DL NERSP can do wavelengths from the red, infrared, 1 micron, all the way down to about 500. 500 nanometers, so you have a broad wavelength range there. So, should come back here. There we are. And so you have this drift, as I'm looking at different wavelengths with this little tiny cutout, I can see drifts during the course of the day. Down here is time, 60, 70 minutes here. This was, for a specific day, 21st of June. And so I can see different sort of trends, and, how to line these up will be a bigger problem than how to line up nice big images like from VBI or CryoNERSP or VTF. And so, yeah, these things will sort of drift across each other. So how do we do this with something like an imaging instrument? Well, so this is a quick exercise here that will hopefully give you hope. That I think will show you how we can calculate this, and we can run this on the server, and you can try looking at the offsets here with different wavelengths. We have the white light images. Those are at 7,200 angstroms, so off towards the red. We have G-band, 430 nanometers, 4,305 angstroms. So that's about 300 nanometer difference, so a significant difference in wavelength. And then we have another continuum here down about just about 20 nanometers shorter. And so the effects of the dispersion are going to be smaller between these two wavelengths. And so basically this program here, calculate offsets, will run through and take all the level C images that are on the file system there and calculate the offsets, just do a cross correlation. So we can do this because both of them are continuum granulation images, so the cross correlation works in this case. And so you can run that, and it takes a few minutes to run through and load all the images and do this cross correlation. If you're bored and you don't want to sit there and watch it churn through, or it might get a little slow if everyone's trying to do this at the same time, first, if you set this variable restore shifts first and then run this program, it'll just restore the shifts that I previously calculated on there. And they should be the same values. So, but you can validate later that I haven't made up values. But so yeah, if you want to make sure you source this that home workshop IDL environment beforehand, so you find the directories for everything. Mm-hmm. And then once you do that, there's another program here called plot offsets, which will allow you to choose between any two of these channels. We'll heckle you if you choose something that's not on that list. And it will then plot the offsets in the east-west. So when we do those offsets between the two images, they're lined up with solar north, so we have an east-west and a north-south offset. And so we can plot both of those. The other thing this program does is it calculates the actual atmospheric dispersion for these different wavelengths, or it calculates the magnitude of the refraction at each of these three wavelengths, and then takes the difference and says, okay, your images should be shifted by this much. It uses the location of the observatory and the time in order to figure out where the sun was when you were observing at any given time. And so then that gives it the elevation. And then so that's what allows it to calculate the dispersion for this specific case at the specific time and specific solar elevation. And then it should throw a plot up that shows the calculated shifts and then overplots those the calculated dispersion. So as you'll see, what the early in the morning, and we started early in this case because we wanted that long time series for the gravity wave observations, but we wanted to capture as much of the good seeing as possible. So we try to, you always try to start as early as possible. And so, in the morning it was, 1.2 arc seconds here. This is between the white light and the 7200 and the G band. So it's 1.2 arc seconds in the east-west direction, 1.6 or more in the north-south direction. So over 2 arc seconds, almost of total shift between these two images. These were lower resolution. We only had a 0.1 arc second approximately resolution. So that was only, 25 pixels off. So as you saw, that is very significant. Even at the current scales, this will remain the same, still 2 arc seconds, 3 arc seconds for DKIST, which is now, a factor of 5 bigger. So now we're, 100 pixels off. So it's a significant thing. But there is hope because, right, we have this red line here is the calculation, just using a fairly simple calculation for what the refraction is at these different wavelengths. And you see it does behave pretty well. It behaves as expected. And so we're able to calculate. So again, for this, we have G-band and continuum at 7200. We can just do a cross correlation, and we could line them up that way. That wouldn't work, of course, for the calcium K or for the H alpha or something. For that, we would just have to blindly, we'll have to calculate what the dispersion offset is and apply that to the data. But the fact this is pretty close is reassuring. It isn't as close as I would like there. That's a little bit off, but this is, it's a few hundredths of an arc second error, which is more than I'm comfortable with, but it'll have to do. So here, this is the G-band, even the G-band to the 4170 continuum, so just very close in wavelength, and now the offsets you see are quite small, just 0.1 angstrom, 0.1 arc second, 0.2 arc seconds in this direction. There seems to be some sort of bias here, just a bulk offset. Some of that may be residual errors in the alignment of that grid or something. That's that's a less about a tenth, no, 0.2 of a pixel error in the alignment. So you're starting to see the limits of the alignment of some of those internal calibrations as well, perhaps. But so the dispersion is a problem. It's going to be easiest to deal with it with images, with VBI, and with this kind of data. So you'll lose maybe a little bit at the edges of your field of view when you do this alignment. But as you saw, issues with other instruments like DL-NIRSP or VISP are going to be much more problematic to deal with. So it is a very tractable problem here for imaging instruments. So we should be able to get a precise co-alignment with that. So yeah, and then we can look and see what the final effect is here. So here we are. We have our G-band and our white light image lined up. See, they're pretty close there. Let's see the 4170. And that's the continuum now at the 4170. That's the IBIS white light. So now, see, they're all, looks to be the same image scale. They're all lined up. And now we can track bright points and everything and start to do the science. Okay. Does anybody have any questions? Does this seem possible? Does it seem impossible?
Is there a slight rotation between those?
It's always hard when there's a border because your eye sort of. The question was, maybe there's a slight rotation, possibly. It shouldn't be the border when you're doing things and you have borders and things like that. Your eye often tricks you. Yeah.
But maybe that's what the difference between the red line and the white line is?
There could be that difference, yeah. It's also, I didn't do a sub-pixel interpolation here, so there may be up to a half a pixel offset, which is actually visible if you don't.
On this really low resolution screen, especially.
It's still a 1K. They're 1K images, and it's a 1K screen. So, okay. So again, there's all the exercises. The way this was done is all there. Feel free to poke at it some more, or come to me if it doesn't work. And if you have any questions. So I don't know. Everybody's good? And again, so these data are on there. You have level C. All you have to do is apply that dispersion correction. Level C is pre-dispersion correction. So all the plate scales are nominally the same. They're lined up according to the grid, but they haven't had this dispersion correction applied.
So when you have wavelengths that are very, very different,
Right.
you trust your numbers.
If the image is different between the two, yes, you just have to trust your dispersion calculation and use that. Luckily, it seems like they are reliable enough. But I think that's it. I don't think that's enough.